Hello. This is where we had left off in class on Monday. We were looking at a horizontally oscillating spring sort of across a frictionless surface, so it wouldn't be slowed down by the surface at all. And we had determined that the equation of motion should be given by x equals a cosine omega t, where omega would have to be the square root of k over m. And so omega is called the angular frequency or angular velocity. Either one is okay, but do include the word angular in front of that. But what we want to look at for today is what happens if we go vertical. Okay, so we were looking horizontally at what would happen, but let's figure out what happens if we go vertically. All right. So if we go vertically, there are a couple of things that really come into play. Okay, the first of those is that we have to look at something we'll call this L naught, which is the rest length of the spring. X, which we've already talked about, will be the stretch from equilibrium. Okay, so we're going to have to consider that. We're going to have to consider where is equilibrium going to be. And then we'll look at oscillations around that, okay? And actually, let's see, we're going to introduce one other variable, xeq, which will be the stretch to equilibrium, okay? And we'll see why we need that in just a moment. Okay, so we have the rest length of the spring itself. Okay, that's how long it is when there's nothing pulling on it. You have, probably I should have put the stretch to equilibrium first, and then there's the stretch from equilibrium that could also occur. Okay, so let me draw a little series of pictures here. Okay, so let's say we have up here a top, and down here we have the floor or the ground, and that's where y will equal 0. And initially, if you were to hang the spring from the top, it would just hang something like this, and it would have a length, which would be that L naught, the rest length, L0 or L naught, okay? But then if we hang a weight on it, it's going to stretch down a little bit further. Now, what we're going to assume first is that when we hang this weight on here, it's now at rest. So this will put it right at this height here, which will be y eq. Okay, so that will be the equilibrium height of this. Okay, now some special things will happen there, but you'll notice, here's this line here, which was the rest length. We're adding on to the rest length an amount of stretch, which I will call the stretch to equilibrium, xeq. All right. Now, what's going to happen there? This is important as we're trying to do calculations. At this point, there are forces on the mass. Remember, we pretended the spring has no mass at all. So in the first picture to the left, there would really be no force on it. That's sort of the ideal case, which isn't quite reality. But we'll assume almost all of the mass is in the block. So we have the force of gravity, which is equal to mg downward. And then because we stretched, we're going to have a force that is going to be k xeq upward, because xeq is the amount that the spring stretched. So when you're doing problems where you're trying to figure out things about where equilibrium will be, you can say that mg is equal to k times xeq. Okay, that equation right there would allow you to solve for k if you knew what the mass was and you knew how far it stretched, or if you knew the mass and you knew k, then you could solve for how far it would stretch. So one of those things would be unknown. And continuing onward though, let's say that in addition to stretching it downward like that, once we're at equilibrium, let's say we pull it down even further. Okay, you'll notice in the second picture, I tried to draw mg and k xeq to be the same size. Now, what's going to happen if you pull it down? Hopefully you understand it's going to want to move upward. Okay. Now we have an additional stretch here. So in addition to all of the other stretches, I'm going to label this as just X. Notice that's how far we stretched down from equilibrium. Okay, so we've stretched an additional X. I guess I should have that line YEQ probably running through the top of the block. But basically we go not through the middle of the block like I showed in the previous picture, but where the bottom of the spring is would be a good location for that. As long as we consistently measure to the same place, we're okay. So we pull this down further and we're going to release the weight. All right. Well, we know that it's going to want to go up to equilibrium. Now, well, why is that? We're going to have a force upward on this thing, which is K times the total amount that it's stretched from its rest length. So it would be KXEQ plus X. All right. Whereas downward, we're still just going to have that the force of gravity is equal to mg. So we now have an upward force that is greater than the downward force. So it will want to go up to equilibrium. Now, it'll continue because it will have velocity when it reaches equilibrium, or in kinetic energy, it will pass through equilibrium, and then it will be above equilibrium. And when that's true, when we get to that point, then K times XEQ plus X will actually be less than mg, and it will want to come down again. Okay, so remember, at equilibrium is where these forces completely balance. When we're below equilibrium, the stretch is greater, and so the K times the total stretch will be bigger than mg. When we're above equilibrium, it will be less than that, so the object will want to keep bouncing around equilibrium. Okay. Now, let's try to figure out what's going to happen as we do this. Okay, so if we consider the third picture here, we know that F net should equal ma. Well, if we look at the third picture, the net force is K times XEQ plus X minus mg. Okay, the first term is the upward force, which we'll assume is positive, minus mg because it's downward. That has to equal ma. Okay, now let's continue with this. Let's distribute the K. So KXEQ plus KX minus mg is equal to ma. And then let me rearrange this. Let me say KX plus KXEQ minus mg is equal to ma. Well, look at this term right here and what we had above. KXEQ, or maybe look at the picture right over here. KXEQ and mg should be the same size. So those actually go away, okay? So if we simply look at the stretch from the equilibrium point, we can still say the following. Remember, this was the formula that we had when we were working with the horizontal oscillator. We can still say that Kx equals ma, but note what x is. It's the distance from equilibrium, or the displacement from equilibrium. It's not how much the spring has stretched in total, it's just the stretch from equilibrium. So notice that mg, gravity, is now missing, all right? So the force at equilibrium, maybe the spring force at equilibrium, cancels gravity. So we can analyze the system without considering gravity at all if we simply measure what's happening, the displacement from equilibrium. Now, if this is still true, then we can get back to Kx is equal to mx double dot, okay, or the second derivative of x, which is acceleration. And then that means the solution is still x equals a cosine omega t, where omega is equal to the square root of k over m. All right. Now, when you get into the MATLAB code later, you're going to see that what we do, we talk about the y values, and we need an equation for y. And so we're going to say y is equal to basically a cosine omega t plus y EQ. Okay, so the y value at any given time is equal to the displacement, the amount that we've stretched from equilibrium plus where the equilibrium value is. Okay, you could also say that a cosine omega t must be y minus YEQ, which would just be x. This will be the stretch from equilibrium. So at some points in the MATLAB code, instead of seeing kx, you will see, so if you see k times y minus YEQ, that's the same as having kx, all right? So this equation right here would describe the vertical oscillations. It's just like the horizontal oscillations, except you're going to have to add in an equilibrium height if you're calling the ground 0. Okay, so that should prepare you for what you need to do for part 2 of your lesson tonight.